next thing we're talking about is called uniform circular motion, or UCM for short. Okay, and so it's really just about things moving in a circle at a constant speed. Okay, and so a couple things here. First of all, I want to think about the fact that velocity is a vector, okay, which means it has both magnitude and direction. Well, if something is moving around a circle, then that direction, the direction of its motion, is constantly changing. Okay, and so a lot of times we're going to talk about speed, because the velocity, the speed as you rotate is constant, but the velocity is not. The velocity is constantly changing. Okay, but we can approximate, we can find kind of like a measurement of the velocity at any instant, at least the magnitude of it, by dividing the distance it has to travel around the circle by the time it takes to make one revolution. So if this is the radius of the circle, we can actually calculate how far around it has to go. Okay, you learned this in your, probably your, I don't even know when you learned that. But anyway, circumference of a circle, 2 pi r. Okay, and then the time around the circle is something we call the period. So the time for one revolution is called the period. So T, capital T, is equal to the period, which is the time for, there's no E in 4, by the way, for one revolution. Okay, so this is equal to 2 pi r over T. And we'll call this the period equation. So T is equal to then 2 pi r over V. And so this is the version we'll see most often. And so this shows the relationship between the radius, the velocity of a particle, and the period, or the time for one revolution. So this is the period formula for an object in uniform circular motion. Okay? So if you take a look here, this is an activity where we can kind of simulate uniform circular motion. And so what I want you to think about is that for things like velocity is a vector, meaning it's going to make, like, direction is a factor. And so when something is going in a circle, we actually see that direction changing. So if we draw the velocity vector, make it a little bigger so you can see a little better, we can see that changing. Okay, and so we see that velocity vector changing as it goes around the circle. Okay, we'll also increase the radius so it goes a little slow. Okay, so V, the length of it stays the same, but the direction of it changes. You can see it's tangent to that circle. Okay, and so what happens here is there's an acceleration vector pointing in the direction of the change in velocity. So at any moment, this particle wants to continue going this way, but it's getting kind of pulled inward, okay, as it's prevented from going that way. And so instead of ending up here, it ends up here. And then it wants to keep going like this, and it gets pulled inward again. And so it ends up here instead. And then it's trying to go here, it gets pulled inward, ends up here. And that happens all the way around the circle. Okay, so there's this particle that experiences acceleration constantly. It's constantly accelerating because it's constantly changing direction. And so the direction of that acceleration is towards the center of the circle. And so here you can see it's always getting changed towards the center of the circle. The acceleration is almost like a pull. Something's pulling it towards the center. Okay, so what we call this acceleration is centripetal acceleration. Okay, centripetal means like center seeking. So this particle has a centripetal or center seeking acceleration that causes it to rotate like this, okay, in a circle. And we can actually quantify that acceleration. We can actually find how strong that acceleration is. Okay, so we can calculate centripetal acceleration by taking the velocity and squaring it, and dividing it by the radius. Now I'm not going to derive this equation for you. There is a derivation in the book if you want to look at it. Most equations I will derive, but we're not going to do this one. Okay, but so this shows basically for something to be moving in a circle, this shows how the relationship between how strong the acceleration is to cause a object with velocity v squared divided by r. Okay, and so this is how the acceleration relates to the velocity and the radius, is essentially what this is. And so that means that an object going faster will experience more or less acceleration. It experiences more because we have v squared here, so we're taking the value of v and we're squaring it. It's on top here. Okay, an object with a larger radius will experience more or less acceleration. Will experience less. The bigger r gets, the smaller the value for a. It's easier to rotate something that is further away than something that is up close. Okay, if something's really close in, it's going to have to change its direction much faster. If it's really far away, it can change its direction much more slowly. Okay, and that's basically what it comes down to, this equation here for centripetal acceleration. Okay, and so now we'll kind of look at how those changes work out. Okay, so we're back to here, and we have this example here. So if I decrease v, what's going to happen to a? Well, a should, as I decrease v, you should see a getting smaller there. Okay, and as it increases, a gets bigger again. So smaller speed means less acceleration required. Greater speed means more acceleration required. Okay, what will happen to a as I decrease the radius of the rotation? When we try it and we see that as this gets smaller, a gets bigger because it has to change that direction faster. Okay, we'll decrease the speed, so you can see it go a little slower. Okay, as the speed gets bigger, so does a. As the speed gets smaller, so does a. Okay, and this is basically it. This is uniform circular motion. Okay, so now we're going to actually explore a couple scenarios. Here's when we have a pilot with a speed of 684 meters per second. That would be their velocity, 684. We have a radius of 5.8 kilometers or 5,800 meters. And the question is, what is their acceleration? So what would be their centripetal acceleration? Well, centripetal acceleration is equal to v squared over r. So we know v, we know r. Go ahead and calculate what their centripetal acceleration would be. You should have gotten about 80.7 meters per second squared of acceleration. Okay, this is quite a bit of acceleration. That's about, so sometimes, especially like with pilots, they measure acceleration in terms of how many times acceleration from gravity. So if you divide that by 9.8, you could find that out. So dividing it by 9.8, we get like 8.2 G's of acceleration, or 8.2 times the acceleration from gravity. And 8.2 G's is a lot. That's a lot of acceleration. That would be at, that pilot was probably getting close to passing out there. Okay, it's definitely pretty much near the limit of what a human can like stay conscious for. So at least for an extended period of time. We're going to look at one more example, and then we'll practice the rest in class. Alright, so for this next one, I want to know the centripetal acceleration of the second hand on a, let's say on a wristwatch. So the second hand on a wristwatch. Okay, so we need to know a couple things though, right? So centripetal acceleration, v squared over r. We need to know v, and we need to know r. So we'll estimate r maybe to be, let's see if it's a wristwatch, maybe it'd be like 1.5 centimeters. We'll say 1.7 centimeters. So in terms of meters, that would be 0.017 meters. Okay, now we need to find v. Well, we don't know it, but we do know the relationship between period, radius, and velocity. Okay, which means that velocity would be equal to 2 pi r over t. So we could swap these when that one's on the bottom. Well, we know that r is 0.017, and t, for the time that it takes to complete one full rotation, the second hand would be 60 seconds. Okay, so that'd be equal to 2 pi times 0.017 over 60 seconds. So we end up with about 0.00178 meters per second. And so from there, I want you to go ahead and find what the centripetal acceleration would be. Okay, so I ended up with something like 0.0018 meters per second squared. Okay, so from here, there's one other thing I want to do. I actually want to come up with an equation for centripetal acceleration that doesn't use v for velocity. Okay, so I want to get rid of this v. And so we can do this because we have this relationship right here between r, v, and t. So I want you to use this with this and try to come up with an equation for a that doesn't use v. Okay? Alright, so what you would do is you'd put v in here. You'd put this in here for v because v is equal to 2 pi r over t. So that's going to be 2 pi r over t. This is all squared, then that's all over r. So we get 4 pi squared r squared over t squared over r, and then this r will cancel with that squared, and we get a sub c, centripetal acceleration, equal to 4 pi squared times r all over t squared. And if you plug in the value for r and the 60 seconds for t, you should end up with something pretty close to that 0.0018. Okay?